Hello, we have just gone through the graphical solution method and we are able to not just visualize the original LP model, but through it gain some insights into the solutioning process and be able to think, how the solver might actually uh, work out the final solution, the final optimal solution. Right now, we are going to explore a little bit on the um, sensitivity analysis, if I might just use that, because we want to ask the question, to what extent can one of the two coefficients in the objective function change, all right, in such a way that the optimal solution will not change. Now, coming back to our graphical solution workings, we are now basically asking, when we have our objective function drawn at this point, right? So we have found that this is the optimal solution. Now what we want to ask is, to what extent can one of the coefficients change? Let's say we want to change 5. Maybe 5 might become 4.5. 5 might become 5.5, right? Oh, inflation is coming, so boss decides to add 50 cents per table of but the profit to the profit of each table sold. So 5 becomes 5.5. But we don't want to disrupt the production process of 8 tables and 3 chairs every week. So we want to ask the question, to what extent can 5 be changed while holding 2 constant, right? Now that idea is basically asking that when we change 5 to something else, we are changing the gradient of this red line pivoted around or about the optimal solution point. So another way to ask it graphically is that, to what extent can the gradient change, right, so that it will still intersect this 8,3 position, all right, as we move further northeast. Now you might say, well, just go ahead and change. Well, it will always be 8,3, isn't it? Well, yes and no, because you see, as you rotate about this point, it is true that any gradient will do. But then when you rotate beyond this gradient, you find that, hey, wait, as I move, I'm actually touching this point. You see, if my gradient is this way, if the objective function has combinations of coefficients, basically amounting to changing the gradient of the line, if I change the gradient of the line and it becomes this way, you find that no, it will skip past 8,3. In fact, it will no longer be 46, it will be something else. And this point, 4,6, will be the highest, isn't it? So, in other words, what we want to ask is, therefore, to what extent will the gradient stay between, in this case, the gradient of the line x1 equals to 8 and the gradient of the line 3x1 plus 4x2 equals to 36. Okay, so we're going to rewrite this 5x1 plus 2x2. So 5x1, we're just going to call it C1, right? C1 plus 2x2 equals to 10. Okay, and it can be equal to anything. So when we if we call x2 the y-axis, then if we rewrite this as 10 minus C1 divided by 2, and I'm going to divide by 2 separately, we'll find that the gradient is actually simply minus C1 over C2 if this 2 is another gradient. So this minus is always there because of bringing C1 over. All right, and if we change 2 to C2, then we are dividing by C2. Never mind if 10 is divided by C2 here, but what we are interested in is this, times x1. Yeah, so what we are interested in is y equals to intercept plus gradient times x. That's our usual line equation, isn't it? Mx plus c, right? So this is our intercept plus gradient times x. So our x here is represented by x1, and therefore the gradient is represented by minus c1 divided by c2, the other coefficient. So for now in our discussion, we're going to fix the c2. So it's always 2. And our gradient is always negative of the one that we are changing. So here we are changing 5. So the gradient becomes negative C1, because we're going to change 5, change to what? We're going to just call it a generic variable C1. But at any given number, C1 is constant in this case. X1 is the one that is varying. So C1 divided by C2 and then put a negative sign there. So that is our gradient. So minus C1 negative C1 over 2, right, in our example, is the gradient of the objective function line. And the y-intercept is basically to make sure that it is pivoted around that point. Then we want to say that this gradient better be, larger than the gradient of this line, all right? And of course, by the same token, we will know that the gradient of this 3x1 plus 4x2 equals to 36. The gradient of this line will be negative 3 over 4. Negative 3 over 4. So this is infinity line. This is negative gradient. More negative, less negative, less negative. All right, infinity. All right, and very large gradient until very small gradient. Okay, so what we want to say is that this is infinity or negative infinity, depending. And this will be our gradient of the objective function has to be, how should we put it? This is 0, minus 1, minus 2, minus 3. So more and more negative, right? More and more negative infinity. So this is more and more positive. So it has to be less than equal to minus 3 over 4. This is more positive, 0, 0, more positive, more positive, more positive. Let's put it this way: minus infinity, minus infinity. So, well, has to be greater equal to minus infinity. So it will have to be greater than minus infinity, but not more than negative 3 over 4. Okay, because this is less than equal to 0. In a way, we can put it this way, like this. Okay. Now, well, we are not very good at operating with double inequalities, so we're going to split it. And this. So first thing first, we want to handle divide and conquer. This is too complicated. We split it. Right. When we split it, let's do the easier one. Multiply by minus 1. We need to change sign. Okay. And then if we just get rid of the 2 by multiplying by 2, we get multiplying by 2. Okay, so similarly, we have infinity, change sign, C1, and C1 divided by 2. If we times 2 infinity, we still get infinity. That means C1 just can be any number so long as it's not getting to infinity. So, but it cannot be too small. So it has to be at least 3 over 2 or larger. And that's it. So we can say that, well, business competition is flaring up and boss wants to reduce profit, cut the price, and sell more tables. To what extent can we, uh, ensure that we don't change the production process of making 8 tables and 3 chairs every week, while still reducing the price of the table and thereby reducing our profit? So our profit can go down from $5, all right, all the way down to, well, now we know, $1.50. All right, and still the what do you call it? The profit, the optimal solution will not change.